Okay, so it's time to start. Welcome everyone to the third and last day of the ICST conference. So before we starting with the keynote, there are two messages. So one is that this Open Steering Committee meeting will take place from 2 o'clock, and everyone is invited to attend. Open means open. And then the location for that meeting is not as announced in the printer program. I assume most of you know, hopefully all of you. So it will be in the auditorium, or Hörsalen, as it's called in Swedish. So that's the place one floor down and all the way around the corner, so to speak. Okay, so that about the practicalities. So I'm really, really happy to have the honor and pleasure of introducing Professor Marta Kwiatkowska from University of Oxford. She has for some years been working on model checking and probabilistic stochastic models, which is an area that I had some interest in some years back. And now she will talk about an extremely timely topic, I would say. I mean, trying to cover some white space on the map of knowledge, I would say. I mean, these learning-based approaches that are used, for instance, in autonomous driving, or will be used in autonomous driving, how can you ensure that they actually function correctly? This is really an interesting topic. I'm very much looking forward to your talk, and please, go ahead.
Okay. Thank you. Good morning, and thank you for this invitation. So it gives me great pleasure to talk about work that has arisen from collaboration with engineers. I have a large project with engineers working in the Oxford Robotics Institute, and they are actually developing software for self-driving cars and various other types of autonomous systems. And because I have been working in formal verification, trying to prove properties of systems and temporal properties that they hold, I actually got interested in this problem. And what I'm going to talk about is two papers. There was an invited paper at CAV, which is the main verification conference, and there is also another paper which will be presented next week by my student at TACAS, which is the other verification conference. So what I'm going to focus on is neural networks and how we can do formal verification for neural networks. I suppose I don't need to remind you that deep learning has made tremendous advances, and we hear about it all over the news. I think what many people don't realize is that neural networks were actually first proposed in the 40s, and then everything went quiet about them until first convolutional nets were proposed in 1998, and then deep nets were trained in 2006. So if you think about it, this is only just about 12 years since they were trained. Then ReLU nodes were introduced to improve training, and in 2015 we had the vision breakthrough, and 2016 they won at Go against a human player. So why now? Well, of course, this is because of big data. There is big data, and moreover, there is lots of labeled data. All these Instagram pictures of cats and dogs, etc., they are actually being used now for training. On top of that, the programming of neural networks is done at a very high level. The models are very flexible. If you've ever done it, you know it's only a few lines of code. It then takes 2 weeks to train the network, but programming itself is easy. And of course, also, because these neural networks are compute hungry, at the same time, the technology has made great progress. And we have now GPUs and also efficient inference. So because of that, there is much interest from the tech companies. So I prepared this talk before Apple 10, Apple X, which is now doing face verification, but of course there is also Google Translate. There is Alexa. They are all using machine learning and neural networks at the back end. And of course, much more, for example, healthcare. People are getting interested in using image classifiers. And in fact, I'm quoting this software that was developed to recognize cats from dogs is being used now for cancer diagnosis, okay? I mean, these kinds of statements got me thinking. And then, of course, because of my collaborators, I also got interested in what automotive industry is doing. What I'm showing you here is a picture of an Nvidia car. This one is driving around roads in California. I actually had a ride in the car in New Jersey. They are also testing it in New Jersey. As you can see, this car drives itself. What it also does, it recognizes traffic lights, and it goes on green, and presumably stops on red, etc. And they've even taken it to Lombard Street. If you've been to San Francisco, you know what I'm talking about. So this person is Urs Müller, and Urs Müller proposed the neural network that actually drives this car. And he is now in Nvidia in New Jersey. Okay, so I will just summarize now what you have seen. Okay, so you have seen a car driving itself, but in fact, what this car has is a controller, and this is an end-to-end controller. End-to-end meaning that it starts with camera images, and it's a neural network that then produces steering controls. It has been published. It's called PilotNet, and at the moment, it is not a recurrent net, so it doesn't have memory, so it only does lane keeping and lane changing. And it runs on an Nvidia piece of kit that you see here in the right-hand corner, okay? It's a GPU sitting in the car. But what you have also seen is you have seen the traffic sign recognition. That is not at the moment done using neural networks, but we know, I mean, in the Nvidia car, but we know that it is possible to do it, and in fact, that's what my talk is going to focus about. So I'm not talking about what's in the Nvidia car, I'm talking about the potential of what, you know, people might be putting in order to recognize traffic signs. But if you know about neural networks, you also know that they don't come with any guarantees. It's just something that is very little discussed. So just to set the scene, what your car may be seeing is these types of images. Okay, this is an image. This one is from ImageNet, but of course it could be, you know, the camera image. The one on the left is classified as a red light, but these others are, well, we've changed some pixels. You can probably not see where, but they are all misclassified. Okay. Now, here I'm seeing you some more complex pictures. There was a Nexa challenge where they've taken a lot of these images using the dashboard camera and set up a challenge to come up with a neural network that would produce the classifications. And what I'm showing you is what we have done with our software. If you take something that classifies as green, okay, you can then, as a red, it's classified as red. If you find one pixel, change it to green, just one pixel. It will change the classification of the network to green. Okay, and if you are sitting in that car, you might be worried a little bit. So what we have also done is some other kinds of exercises. This is the German traffic sign benchmark. Okay, in Germany, they use kilometers. This is presented for the British audience. So you can see a stop sign changed to a speed limit, and go right changed to go straight. This is just by manipulating these images. And this is with this very, very high confidence. Okay, because neural networks produce via softmax with every classification something that is called confidence. But in fact, that confidence is not the probability of the classification being correct. Okay, so you might say, well, but these are, all artificial problems, because I've taken some images of traffic signs, I've manipulated them, and okay, yes, the networks don't have to behave correctly on those, as long as they behave correctly on, real images. So just the week before I was giving the keynote at CAV, there was this tweet about Tesla. If you've been driving around California on the 101 highway, it has misread the 105 speed limit at that junction, okay? It has read the 101 sign and misread it as a 105 speed limit, 105 miles. And of course, this is a very extremely timely topic. Just in the last 3 weeks, we had news about an Uber crash with a pedestrian. We also had news about another Tesla. This is a Tesla crash, and it comes from exactly the same stretch of the motorway, the 101 highway. And this is still under the investigation, so I will not say any more, other than this is perhaps a real problem, more real than it, may seem from my artificial examples. Okay, so why? How can this happen if we have 99.9% accuracy? Okay, this is what these neural networks are claimed to do. Well, because neural networks are unstable with respect to adversarial perturbations. And this is something that the machine learning community has known since 2014, but somehow because of the excitement that they are working, and the performance. I mean, I don't know if you've ever tried speech recognition software, which I did about 15 years ago, and now Alexa, it's just a dream. Yeah, I can understand that people are getting excited about it, but I think with excitement, we also need to stop and think. Now, what adversarial perturbations are modifications to the image, and sometimes they are imperceptible to a human. So if you add this type of noise to the panda, it will then be classified as a gibbon. Okay. So this can be artificial white noise. What you've seen in my images is actually modifications which can correspond, for example, to wear and tear, or perhaps even change in lighting conditions, shadows, etc. These also have to be considered. But they are a very practical risk, and they are also a security risk if someone can intercept the camera feed and introduce modifications. So these are being studied now in the security community. Now these are on top of that transferable. That means that you take the same image and try it on a different network trained on different data, and it will still throw the network. So there is something fundamental going on, but people don't understand it yet. I mean, of course, risk in the sense of the probability of misclassification is something that has been studied in the machine learning community. And in fact, there is something known as the VC dimension due to Vapnik, which actually defines risk as the probability of misclassification, but because we actually don't know the input distribution, you can't really compute it. So what they do is they compute instead the empirical risk, and this is on the assumption that the distribution of the test data follows the input data, which you don't know, but on that assumption you can then compute it as a weighted summation. So this is not something that you can use for neural networks because of the sheer scale of neural networks. So these approaches have been abandoned, and instead what people are studying is so-called robustness. And this is expectation, so this is a weighted summation of the minimal expected distance to misclassification. Okay, so you can take an image and a modified image, and if you have a vector space, you can compute that distance, and you try to compute. And there are a number of approaches which search for these adversarial examples, that is, which of these modifications will actually throw the network. But what I'm going to talk about is how we can focus on something like classification decisions, and I will be working with image classification because we do have lots of data for that. We also have lots of networks that we can use and we can compare ourselves against. But I'm going to focus on changes that are perceptible because they represent things like changes in lighting conditions, perhaps the angle, snow, shadows, etc. Okay, but the idea is that if I focus on an image and some region around the image, some other images, then what I would expect is that the classification decision will be invariant in that region. Okay, so this is just a very basic property that you can use then as a key to to use in some safety assurance framework. And you can also use it, for example, within explainable AI frameworks, which take neural networks a step further, and instead of just producing a classification decision, they will also give you an explanation why it has been classified like this. So if you're interested, there are 2 papers, and you can follow the link to those papers. Okay, so first of all, this is what a neural network looks like. What you see on the left there is an image. This is an image, in that case, of a car. But this image is actually a point in a vector space. So the image is a 3-dimensional image, a pixel array. But for the color, you also need the 3rd dimension. So these are the points, and I have a vector space with various distances. People tend to work with L2, but also L1, L0, LP in general. And then with a neural network, this is a feed-forward neural network. It has several layers of neurons. It will take this point, and it will transfer it between these layers. And these layers combine a linear transformation then with some activation function. And this activation function can be a sigmoid, but more recently there has been ReLU, which just cuts off all the negative or positive elements. And the idea is that it will pick out the features. It will use also other types of layers. It will pick out the prominent, the salient features in the image, and it will then, on that basis, give you a score. So it will give you a vector, which you can then normalize it as the so-called confidence. And this is, in that case, the confidence tells you that it thinks that it's a car. Okay? But the situation could be you can have, for example, car and truck, very close together. So for my problem setting, I'm just going to assume that I have a vector space giving me these inputs. So each of these points is an image. And then the specification for the problem is actually, in the case of image classification, well, how a human would classify it. Give a human an image, and the human will give you the classification. Oh, yes, car or cat. But then what the network does is the network approximates that human classifier using a neural network trained from labeled data. And labeled data is just a certain set of an image and a classification. Okay? And all these labeled data then fed into the training, and each linear layer then learns the weights and the bias. That happens in the training. So to explain to you what happens in terms of training, this is quite a real situation in machine learning. What you want to do is to classify, and in this case, you see the red dots and the blue crosses. The dotted line is the real task decision boundary. Okay, this is how you divide between these two classes. But then when you train the network, you give it a subset of the data to train for whatever you had, the labels for. So it will train it, and what it will produce is a model decision boundary, but that model decision boundary doesn't have to align. Okay, and this is quite a typical situation there. The model decision boundary doesn't align with the real task decision boundary, and for different models, that is different networks, it will be, even different. So what then happens after training is there is the testing phase. They select a set of test data, and on those test data, they try whether the network classifies according to those classifications. What I'm showing you here, the test data, the darker blue crosses, are points that you choose to test. But if you then push those points towards the task decision boundary, this is where it is very likely that you will find an adversarial example. For the obvious reason, because they don't align there perfectly. So the places where you will find adversarial examples is if you start with a test point and then push, and that's what the gradient stochastic search does, essentially. What you also see is because this is trained on data that is sparse, so you can have 2 points where the network has to interpolate. Okay, but what if there is a crucial data point missing in there? So if you push in between those points, you will also find some more, examples. So this is the situation, and I will show you what we are trying to do with verification. Okay, so what we are focusing on is something that is known as Pointwise Robustness, and was introduced by Segedi, Google in 2014 in the first paper that observed adversarial examples. What is Pointwise Robustness? I'm focusing on individual decisions for now, okay? But then once you have individual decisions, I can then compute the expectation by weighting with respect to the training distribution. Okay, but for now I'm focusing on a single point, and in that point you assume that there is some kind of smoothness region around it of some diameter, and if you can find an adversarial example there, that's bad. If you can't, that's good. Okay, so this is the problem that I want to focus on, and I want to use verification, but this is something that has not been studied much, even though the first paper was proposed in 2010, but at that time they were working with a sigmoid, and with a sigmoid they could only scale up to 6 neurons, okay? And these days we have millions of neurons. So my problem now looks like this. I have this point X, so this is my car, image, and the blue region is, a region where I would expect invariance of the classification to hold. The Y is an adversarial example. It's something that you want to rule out in that region. But of course, this kind of problem raises a whole lot of questions. What should the diameter be? Okay, it has to be small, not too small, obviously, but also not too wide. Certainly should not overlap with another class. because if you find something in the intersection with the other class, it could actually be a true classification. Also, which norm to use? I've mentioned people use L2, they use L1, L0, L sup, LP, okay? But they are actually not perfectly aligned with human perception. What we need is actually proper human perception. But such metrics don't exist yet. And then also, what is an acceptable perturbation and what is an adversarial perturbation? So what is it, that a human will recognize as a shadow or as snow, and at what point it will become something where it should not be classified, as the same scene? So these are all, important problems. For now, I'm focusing on the technical aspect, and what I want to do is I want to show you how far we can go with these types of problems, assuming that someone tells me, the diameter. I can choose a metric, I can work with these metrics, but someone needs to tell me the diameter, but also needs to tell me the manipulations. What are the manipulations? Right, so with this, I'm defining my safety verification problem as where the specification is, it's focused on a single point. I look at a region of images around that point, and I have as a specification a set of manipulations which are the legal manipulations that you can apply on them, okay? And I want to use the pointwise robustness as a safety criterion, okay? That means if I manipulate that point in any way, the classification should remain invariant. But if I find a misclassification, I found an adversarial example. So assuming that you can search this in a finite way, for which we discretize, so assuming that you can search this in a finite way, you have a very basic search-based method to check for adversarial examples. But my search will then come with a guarantee which all the stochastic gradient-based searches do not have. If they find something, they find it. But if they try again, it doesn't mean that for them trying again and again will eventually give a guarantee. For that, you actually need to come up with some kind of coverage criteria, test coverage criteria, which have not yet been developed in that community. So that's what I do, and in terms of that picture where I was showing you before, we do training, we do testing, now we do verification. What I'm trying to do is I'm trying to cover, but exhaustively cover, larger regions of the space around the test points, okay? So assuming I can discretize and assuming I can search, I have a method that will rule out adversarial examples as opposed to an alternative which is a very, very fast stochastic search but doesn't have guarantees. So I have a verification framework. This verification framework has to work with a real-world network, and these have millions of neurons. They have hundreds of thousands of neurons in one layer. So how do you deal with this? I mean, a typical ImageNet image is 2 to 8 times 2 to 8. I mean, the camera images for PilotNet and for any types of kind of automotive simulators are almost the same size. They are 160 times 80 pixels. And so this is the kind of scale that we need to be able to deal with this. So in this first paper, what I'm doing is I'm actually not doing verification on the whole network in one go, but I'm doing it layer by layer in order to divide the problem into smaller problems and hopefully, rule out as you go along more and more adversarial examples. So for me, this is also a dimensionality reduction, and another dimensionality reduction, which is at the moment completely hidden under the hood because I'm not talking about it, is also focusing on the features. And as I've already mentioned, my approach, because it comes with guarantees, it is very different from the heuristic gradient-based search approaches that have been developed in machine learning. And we do compare against them. So from the point of view of the kind of, what it looks like underneath, this is the situation that I'm considering. I have layer 0, which is the input layer, and X is my car image. And then I have to map to each of the following layers. So from some hidden layer, I will have forward maps, which I call phi k, and then we need to map the region to the next region, okay? Now think about it. If I want to take a car and then I want to, for example, introduce snow, or some other kinds of manipulations, I will be doing this in the input layer, and then I will be mapping this, okay, into the network. And how do I check if it is a misclassification? Okay, that I will be mapping both the image and the modified image. I need to feed all the way to the output layer, okay, and check, but I may sometimes also need to ask a human, should this have been misclassified or not? And I will show you some of these examples. And in fact, what I also need, it's not enough for me to be able to map forward, I also need to be able to map backwards, because I need to find out which images the particular manipulation, say I've manipulated in the hidden layer, this particular manipulation has come from. Now for those who know, for the sigmoid, the inverse exists, but for ReLU nodes are just simply max of X and 0. Okay, you do not have a unique pre-image. What you have is a set of images from which misclassification, that a manipulation has come from. But in fact, any of these is then, a source of the problem that needs to be considered. Okay, so this is the situation, and for manipulations, okay, so for manipulations, I'm assuming is that I'm working with a vector space of images, and these manipulations could be things like, okay, I can change the intensity of the picture, of the pixel, I could change the color, I can, for example, deform, you imagine the angle changes, okay? So all these underneath can be represented as maps from pixels to pixels. And in fact, it will probably be some group of operations of varying levels of complexity, but underneath you can represent them as individual pixel changes. Okay? And then I can define the safety of my network at an individual classification decision point with respect to that region, for which I know the diameter and the set of manipulation. It means that if you perturb it according to these manipulations, the classification stays invariant. Okay? And then all I need is to be able to implement it, and I will not tell you how we've done it, but we have done it, and the tool is available, and we do it by propagating the analysis, and that means propagating the region together with the manipulations through the layers, okay, as you go along through the layers. And at each stage, if I map into the deeper layers, I have to refine the image and the manipulations. Okay, so I will now show you some examples. And also where we have taken this work further. So this is MNIST. Everybody has to do something on MNIST. And it's very easy to find these misclassifications on MNIST. So the one on the right, it thinks it's a 0. Okay. What we have also done is we've compared the falsification, which is searching for adversarial examples, against competitor tools from machine learning. And I can show you how we compare. So as you can see, FGSM, fast gradient search method, what it does, it introduces noise to the whole image. What you see there is 7, which the network then misclassifies as 9, but the image is all smeared. But JSMA, which is the salient, it identifies salient features and then tries to manipulate, so it works in a similar way to our tool. In our case, they are both misclassified as 3, but we can actually find a smaller distance. Okay, so we can find a smaller distance to the actual manipulation. And here is another example. This is now the CIFAR data set. Why is it kind of not, not very accurate? This is because what we did is we actually manipulated in the hidden layer. Okay, we found a misclassification, but then we mapped the images back to the input layer. So this is an example of an image around the edge of the boundary of the region. Okay. And as you can see, you have this kind of misclassification. This one, I can show you, is something where this was found completely automatically. And you can understand, why. This is working with the ImageNet. You have a street sign, but it's classified as a birdhouse. And all we've done to it is we've just introduced these manipulations. Okay, in this case, they are rather big blobs, but there would be very similar things where you can, okay, it could be just some perturbation, okay, even in transit, or maybe, some imprecision in the camera. So another example, here you just have 1 pixel change, and it just changes the classification. Okay, this is perhaps not safety critical, because it just thinks it's a different type of the dog, but there are other examples that I will show you next. But here, okay, this is raising another point, because what you see is you have a Labrador retriever on the left, but there is also a lifeboat there. So there is just something in the structure of the labels. And in this case, you cannot, for example, just simply decide, okay, I found an adversarial example, I can then throw it back into retraining. People have done it. You can then overfit to the adversarial examples. You actually need a human to take a look and see, and maybe the actual labels are more involved. Okay, so this is from the first paper. I will show you what we have done since. Well, I mean, as I said, I have a method which gives me guarantees, but that method is essentially based on search. This is what model checking did, more than 30 years ago, essentially search-based. If you discretize, it just, gives you decidability, but it doesn't necessarily give you the performance that you need in practice. So in this example, what you see is you have an image of a tree, and it's got 24 million of dimensions, just one image. And now you need to come up with guarantees, or perhaps you need to find the individual pixel. So it's just impractical to search pixel by pixel. Which is what the first method does under some restrictions. So what we have done instead is we have combined it with techniques from computer vision, And then instead of working on the image, we first process the image by a computer vision technique known as SIFT, and that extracts features from the image, okay? And you can see how, for example, all the background blue is not identified, as a feature. Okay, this is a very well known, very well established method. What it does is it just essentially blurs the image in order to detect the extrema. But this is a method which is invariant to scale, rotation, and translation. So it's a very compact and efficient alternative representation for the images. And in fact, this is something which works in a similar way to the way that deep nets work. Because deep nets, they also extract features, and this little video will show you how these features are extracted and then put together. Okay, so what is this feature? Well, for a 9, it will be the O and the 1. And you can just about see it, okay, on this. But what we have done is we've taken an image, and that image, of course, is then fed into the neural network, where the neural network will extract these features. But I've taken that image, used SIFT. I have an alternative representation, which I can then explore in a black box manner and then query the network in addition to align my features with their features, with the network's features. And what do I do with this? Well, I first use the features to produce a mixture of Gaussian representation, where I use the position of the feature and also its saliency as a weight for a distribution. And when I explore, when I try to search for adversarial examples, I use that weight, so that means that I will be exploring according to the saliency of the feature and not just searching, in a sea of pixels, of that tree. I will be searching here by focusing on the salient features. And the next examples have been constructed using this method. And in fact, what we do is we set up a 2-player stochastic game. So I have my trained neural network trained on images. I extract features using SIFT, and I have the mixture of Gaussian representation. And then I set up a 2-player stochastic game where player 1 will select the feature using the weight of the distribution. So the more salient the feature, the higher the probability that you will explore in that feature. And then the other player will then select pixels within the feature. So the other player selects pixels within the feature, doesn't select pixels in the whole array. And I can set up this game, and I can explore the game tree using MCTS, Monte Carlo tree search, which is actually also the algorithm that was used underneath in the Go playing. But I do not just explore the features that I have extracted. I also query the network to align the probabilities that I've given to the features, okay, just based on SIFT with the actual features that the network sees. And this method is completely black box, okay? That means you don't need to know the weight or the code of the network. And on top of that, it is also very fast, and it gives you convergence to an optimal strategy. And in this case, an optimal strategy would be the optimal adversarial example. And the optimal adversarial example, a lot of the time, is just a single pixel. Those pixels that I've shown you, the single green pixel that forces the red traffic light classification. And it converges over time. So what we have done is we have, for example, you evaluated on the Nexa challenge. Nexa challenge has produced a whole database of these dashboard camera images. They are really very, very complicated images because they are real urban scene. And the point of the channel was to come up with a network which will just simply say, yes, there is a traffic light there and it's green. No, there is no traffic light. But this is the real complexity of the images. Now, there was not ours. There was a winning network which has produced 95% accuracy. Okay, what that means is 95% correct decisions over whatever the test data set was. But what we've done is we've tried that network in our software, and very quickly you can reduce the accuracy of the network to 0%. Okay? I mean, what do I do? Well, I just look at every image in the test data set and set my network on it, and on everyone it found, on average, it finds 3 pixel changes, and on average it takes less than a second to manipulate. Okay. So this is the end of my talk, and I think I wanted to finish with this to somehow, bring the message home that this is, I think, a very important but a very real problem as well. And, we are taking some first steps in the direction to come up with formal verification tools. But really the main message is that I think, all these deep neural networks, they have to be very critically evaluated before they are actually put in any safety critical or security critical applications. I think as we are already discovering, if you just pay attention to the news. Now, of course, my aim has never been to search for adversarial examples. My aim is to rule them out, and I started out with a very basic method. I now have another method which focuses on features and a game-based. I'm also looking at alternative ways to come up with provable guarantees for a given type of network. What is a provable guarantee that it will give you? And to explain, if you think about the pilot net end-to-end controller, can you, for example, have a property that if you manipulate the image a little bit, then the controls are not going to suddenly, for example, force the car off the road, which happens with adversarial examples, but we are just running it, in a simulator. Okay. Okay, so thank you.
Thank you very much. Yes, we have time for questions, and we have a question here.
I loved your talk. That was great. 2 questions. First of all, have you thought of an adversary who knows your algorithm and is trying to game your algorithm? And the second part of the question is probably more relevant to this audience. Have you considered the possibility that the software that you're using to do your neural net computations itself has bugs?
Okay, right. So, okay, the first thing about, the adversary, I tend to release software tools, online. So I don't hide anything about this. But I think it is, adversarial situations, this is a very real problem in security applications. And I think if I came up with a method to defend, then I would not release my software. And I suppose, well, I think it really depends on what kind of access the adversary would have. I think it's always possible that if you give the adversary infinite computational power, then it will find it. So I think the question comes down to, can you limit, the power of the adversary? So I think this is a very good question, and yes, anyone who tries to come up with techniques for defending against adversarial examples in the sense that someone is actually trying to intercept a network and throw something so that, it forces the car off the road. Yeah. Okay, so that's one. And for the other one, I mean, there will always be, bugs in software. And I hope that, say, if you release it, if people start using it, then, people will find them. My software starts with a mathematical theory and a rigorous proof. I mean, until that proof is checked, it's always possible that there will be some small, issues. But I think the general gist of my work is I always start with theory and then I develop it into software.
Yes, thank you for your very interesting talk. My question is that your goal is to provide guarantees, and you contrast that with methods doing falsification. But your guarantees, even though I need to check the details in your paper, are based on a number of strong assumptions regarding the discretization of the problem, the fact that you rely on an imperfect algorithm to recognize features, and other aspects of the work, the fact that your exhaustive search is within certain neighborhood, I mean, in order to end. So, in the end, you are not really, in my opinion, providing guarantees. You are providing guarantees based on a lot of assumptions, and we don't know what the effect of those assumptions are. So, could you comment on that?
Yes, I can comment about that. And I actually have a paper under submission right now, which comes up with proper guarantees. I completely agree with, these observations. This was the first paper, the first two papers, but we have, two more in the pipeline. But I should also point out that there is an approach developed, which I mentioned in my slides at Stanford, which can handle networks of up to 300 ReLU nodes. And it has been used on the neural networks for the ACAS XU, which is the controller for drones, and neural network controller for drones. And this one does provide, rigorous guarantees of, properties, for example. So it works with things like clear of conflict. So it will guarantee that there will be no clear of conflict in some situations. So there are approaches like that. Okay, so this is a parallel talk. At the moment, that one is limited. But I can tell you what we are working on is provable guarantees under Lipschitz conditions.
So, as I understand it, then you're considering a problem where you start with a set of training images, and a network is trained on those images, and then you aim to verify that neighborhoods of those images are classified in the same way. But during the training process of the network, there's no penalty, is there, for putting the border of classification very close to some of those training points? It feels as though one would expect to need to take neighborhoods into account during the training if you want to end up with a robust network that you'll be able to prove things about.
Okay, so I should say that I do not want to compete with people in machine learning who know how best to do training for the networks. At the moment, I'm focusing on a technical problem where I assume that someone gives me, good values for diameters. And also someone tells me, well, I think this is really the critical classification decision. Just think about this red traffic light, okay? I'm assuming those. But from then on, I'm working with a technical problem. But of course, in training, there are all these issues. People have already tried k-means, clustering, for example, to identify, so I think Stanford and NASA, to actually identify these regions and what the diameters should be. So yes, but this would be complementary to what I'm trying to do. I'm giving a formalization of the problem and a very basic, naive solution to it. But then I think we need to take next steps, and we are improving the performance of the techniques and scalability by trying to develop better methods, but for the same original problem.
A very nice presentation.
Thank you.
I have a question. This pointwise robustness, if the training set covers all the scenarios, all the possible scenarios sufficiently, then if you can prove the pointwise robustness of the system, then you can say that the system is robust to all cases. But if the training set is not adequate, then even though if you can prove the pointwise robustness, the system is still vulnerable. So do you believe in the future, would it be possible to test the training set against the possible scenarios and say that the training set is adequate or not?
So there are already techniques called adversarial training techniques that deal with this, so they just improve it. As I said, I do not compete with, people in machine learning. I assume they know what they are doing, but of course these are all very real problems. I mean, if you think about it, as computer scientists, you see, we program and you put in all the assumptions. We have to be very careful about all the assumptions, and in the end, we think about them as sequences of bits. And if you start training a neural network, just imagine what it involves training a neural network for an autonomous driving controller. I mean, what they do, for example, for Nvidia, they collect a lot of images from human-driven cars, okay? But then they've discovered that, of course, because these humans are already good drivers, they would not know, they are never in a situation where they have to react to something, so they have to extend that training data set so that the controller learns, for example, how to go back to the center of the road. Yeah, these are all very important problems. We've shifted the complexity of programming to something completely different. And it's much more complex, much more complex.
Thank you.
I guess we have time for one more question. Oh, sorry.
Thank you for your talk. I was wondering if you have seen or you have done any work in applying adversarial learning on data sets other than image, and what's the state of the art
Other
there?
than images, yes, I have seen. So they've tried it on speech, they've tried it on pose recognition. I think essentially any signal processing, this will adapt. It's just essentially a modification to the signal. So the two that I've seen were, in that domain. And of course, yes, image recognition, just think face recognition. I suppose the majority of the work is in security, and because it is in security, it is often sanitized, and it's sanitized to sort of, in the same way as I'm doing it, to something like ImageNet, because you have a lot of data, high-quality data, high-quality network, so it's very easy to work in that space. But of course, the methods are applicable to other situations.
Okay, thank you very much. I just would like.
Thank you.